Alright, so when you're ready, we're looking back at the transformations of quadratic functions, which was in Optima's shop, was when we talked about this back in Unit 4 in Module 3 book. The goal is to describe the transformations that have occurred from the parent graph f of x equals x squared to this new graph h of x equals negative 3 times x plus 4 squared minus 5. So we have a couple different options. We could make a table, we could make a graph, we could describe it using just the equation. My first go-to was a graph. I looked at both the parent graph and the new graph to see what was happening. And if you remember correctly, transformations describe what's going on with the vertex as well as the vertical stretch. So those are the two things we are really wanting to focus on. When we do our vertex, we notice that we move from 0, 0 to negative 4, negative 5, which is 4 jumps left of 0 and 5 jumps down from 0, as you can see with my little blue jump marks. And our vertical stretch is going to be down 3 and over 1, as you can see in the drawing. And that changes from just up 1 over 1. So our vertical stretch is negative 3. This negative is also evident because we flip from concave up to concave down. But if you are not interested in using the graph or want to know exactly how to get it straight from the equation, we can look at the general form of the equation, a times x minus h squared plus k. And the parent graph has all these invisible numbers in there. X squared gives us an a of 1, an h of 0, and a k of 0. So our vertex is going to be found by looking at the hk, that's 0, 0. And the vertical stretch is going to be found by looking at the a, which is 1. So that's our apparent graph. So we want to think about how it changes from that. And so then our new graph is the h is going to be negative 4, and this arrow shows us that there's a negative in the general form, so we have to change the sign in this specific form. So it's plus 4 inside the parentheses, but becomes negative 4. And then the k is negative 5 because there's a positive in the general form, so the sign remains the same. So negative 5 is our vertex, our k. And then our vertical stretch is found from the a value, and so that's negative 3. So that means that we are shifting left 4, down 5, flipping to concave down because of that negative in the a, and vertically stretched by 3. So those are the transformations we saw in the graph, but it's good to know that we can get it straight from the equation. This equation is standard form, and the standard form equation is a little bit harder to figure out the vertex immediately since it's not in vertex form. So again, my first move was to make a parent graph and a regular graph that shows how it's being shifted, and look at those vertices and those shifts so we can see, or stretches, so we can see that the vertex moves from 0, 0 to 3, negative 4. So our movement is going to be right 3, down 4. And the next point up on the graph is only 1 and 1 away, so our vertical stretch is still 1. So we can say our transformations were right 3, down 4, and no change in the vertical stretch. But if you are a person that wants to know how to do it using an equation, we also learned in Optima's shop how to use completing the square to create vertex form from standard form. So we took that x squared, put it in our top left corner. We took our negative 6 and divided it by 2 to create a square of equal lengths on each side. And we got that x minus 3 and x minus 3 are our side lengths based on that movement. Negative 3 times negative 3 is 9. Well, if you notice, 9 is not 5, which is what we want in our original graph or equation. And so we have to adjust for that. So we're going to subtract 4 to give us that 5 that we're looking for. So that means that when we write our equation using the side lengths, x minus 3 squared, from that x minus 3 times x minus 3 on the sides of our square, we introduce a 9 into our equation that we don't want there, and so we're going to subtract out that 4 to get back to 5. So our k is 3 and our h is 3 and our k is negative 4, so we're going to move right 3 and down 4. Then the last form that they give us is factored form. Again, not obvious what the vertex is going to be, so graphing was my first strategy. I labeled my vertex and my first points to see what the vertical stretch would be. My vertex is -1, -16, which changes left 1, down 16, and my vertical stretch is still 1 over 1. So I know that the transformations are left 1, down 16, and no change in the vertical stretch. But again, if you want to not use the graph and use some other way, the factored form gives us the x-intercepts by figuring out how each part is equal to 0, so that y is equal to 0, or p of x is equal to 0. So that gives us an x of 3 and an x of -5, which if we put on our graph, it's going to be at -5, 0, and 3, 0. And so we want to find the halfway point. We can either do that algebraically by doing 3 plus 5 equals 8. That's the full distance between them. Then divide by 2. That is the distance to the halfway point. It's 4. And then we add 4 to -5 because we're going to the right in that direction. And that gives us -1. Or we subtract 4 from 3 and also get -1. So in our on our graph, you can see that here. If we go 4 to the right, we'll land at a halfway point and should be able to go 4 to the left from here. Oh wow, sorry. 1, 2, 3, 4. So that -1 is going to be our halfway point, our axis of symmetry. And so then we can just plug that -1 into our equation, as you see at the bottom there, and get -1 minus 3 times -1 plus 5, which gives us -4 times 4, which is equal to -16. And so again, we get that vertex of -1, -16, which means that we're moving left 1 and down 16, as we saw on our graph. In the set, we're interpreting and solving problems involving a square root and inverse variation relationships. So the first one I'm going to look at is an inverse variation relationship from your task today. We're using multiple representations to solve each problem. So that is table, graph, equation, everything that you can think of. In this case, we're looking at a kickboxing force that is needed to break a board, which varies inversely with the length of the board. And so we're given that if it takes 5 pounds of pressure to break a board 2 feet long, we want to know how many pounds of pressure will break a board that is 6 feet long. So our first need is to find the constant that goes with this inverse relationship. And so we're looking at varies inversely with, which means y equals k divided by x. In this case, that is going to be force equals k divided by length, because the force varies inversely with the length. K is a constant, and so we're going to plug in a set of length and force values that correspond. They give us 5 pounds of pressure and 2 feet long. So we're going to put in 5 for force and 2 for length. And we are going to solve for k by multiplying both sides by 2 and get 10 equals k. So therefore, force equals 10 over length. And so if we want to graph that, it's y equals 10 over x. So in our Desmos graph, we plug in y equals 10 over x and get this table. We can generate a table and a graph that way. You can also generate a table on your paper and a graph on your paper by doing the same thing. We are interested again in how much pressure it would take to break a board 6 feet long. So we go to x equals 6 because our length is x. And we find that 1.67 is going to be the amount of pressure we need to break a board 6 feet long. And we can, of course, apply any pressure above that to break a board 6 feet long. The next one we're going to look at is also from your task. The distance a person can see to their horizon must be approximated by the function d of h equals the square root of 1.5h, where d represents the distance in miles and h represents the height in the person above sea level in feet. Jacob is standing at the top of Mount Mitchell, which is the highest peak in the U.S., and the top of Mount Mitchell is 6,684 feet above sea level. Jacob's eye level is 6 feet from the ground, so how far can Jacob see? So first off, let's visualize this situation. Jacob is on top of Mount Mitchell, and Mount Mitchell is 6,684 feet. Jacob is 6 feet. So total, his height is 6 plus 6,684, which is 6,690. So then we can plug that into our equation, square root of 1.5 times height, so 6,690. Plug that into the calculator, get 100.17485. Or we can graph this. Graphing looks like this on Desmos. You can see in here that they did a 0.5 exponent for the square root. That's a reminder from last unit, Unit 5, where we talked about square roots being the same as fractional or decimal exponents. And went to 6,690 and found that the height there, or the eye distance, the eye level is 100.175. Or you could create a table and go take a look at those values around 6,690 and see where that exact distance is. Finally, in the Go, we're doing transformations of geometric figures. So you're writing the transformation of triangle ABC in function notation. And the function notation is XY arrow something something based on what pattern you're noticing. If you see this and you're like, oh, I know this is a 90-degree rotation around the origin, then you can easily do your function notation equation, and you don't need me anymore because you know it already. But if you don't know it anymore, or know it yet, the first thing we can do is find the points and write them out. So I've got h is at -3, 1, h prime is at -1, -3, g is at -2, -2, g prime is at 2, -2, and f is at -4, -2, f prime is at 2, -4. I notice a pattern that these coordinates are switching, and then the first one becomes negative. So I'm going to write that in my xy terms. So xy switches to yx, and then the first one becomes negative, which means that my original y is becoming negative. So negative y, comma, positive x. Then they also give us some rules, and we have to describe the transformations. This is a translation that's moving left 3 in the x direction and up 5 in the y direction, which I can just know off the top of my head. But if I don't, then I can pick numbers and see what happens on the graph. So in my case, I picked 2, 4, and 3, 5. Always pick at least 2 points so that you can notice the pattern. Otherwise, it could be multiple things. 2 minus 3 is plugged in. The 2 is plugged in for x, and then the y is plugged in for y, 4 plus 5, and that gives us -1, 9. Then we do the same thing for 3, 5. Put that on our graph. Notice that in both cases it's moving up 5 and left 3. And so we can say, oh yeah, I know this is a translation that's moving left 3 in the x direction, up 5 in the y direction. Similarly, with a problem like this, f of xy becomes -xy, we could just know that there's a rule that reflects the point across the y-axis. But if you don't remember that, then you can plug in numbers and see what happens on the graph. Again, pick 2 points. I plugged in 2, 3, and 3, 7, so I could see some space between them. I got -2, 3 based on my rule. So I plugged that on the graph. I noticed there's 12 jumps and 8 jumps, so this couldn't possibly be a translation rule, but that there's 4 jumps on each side of the y-axis, and then 6 jumps on each side of the y-axis at 3, 7. And so I know that this is a reflection across y-axis because the distance on either side is equal and the line made